So today we're going to start looking at what's called right triangle trig. So you probably did a little bit of this in geometry last year. If you've studied like opposite, adjacent, hypotenuse, that's what section 6.5 is all about. All right. So first we're just going to review a little bit of stuff from geometry, starting with what a right triangle is. Somebody tell me, what's a right triangle? Yeah. Right, it's a triangle that has a 90-degree angle in it. Exactly. Now, there's a name for the side that's across from the 90-degree angle, but we use the word opposite. Anyone tell me the name of that side? It's your hypotenuse. And then what about the names of the other two sides that are shorter? They're called so specifically, you might call one of them adjacent, but there's a general term that describes both of them. But we'll get into adjacent later on, Zach.
Legs.
The legs. Yep. So hypotenuse is across from the 90. The legs are the short size. Here's a picture of what you guys basically just said. Now, when we label sides in a triangle, we use English alphabet letters. The most common ones are A, B, C. A and B are the legs. C is the hypotenuse. Now, that angle that I've labeled here with the Greek letter theta, and I have an arrow, I'm saying that that angle is always between 0 and 90. So is this angle up at the top. How come? How come, even without any other information in this problem, you can be guaranteed that this angle I'm pointing to is 90 or less? Actually, less. It has to be less than. How come?
If it was larger, you wouldn't have three angles. Or you couldn't have you already have a 90-degree angle.
But why does that have to be an acute angle? Yep.
Because all the angles have to add up to 180.
Right. All the angles have to add up to 180, and in a right triangle, you've already used up 90. So together, the other two also have to add up to 90. Okay. We're going to mention this in a second. Does anyone remember what that's called? Two angles that add up to 90? Yeah?
Complementary?
Yep, complementary. How about two angles that add up to 180? Supplementary. We're going to mention those in a little bit. So a theorem here that you can use, and this theorem only applies to right triangles, is a squared plus b squared equals c squared. Now, if you don't use the letters a, b, and c, it's important to understand what the idea is behind that theorem. The idea is you can take a leg and square it, plus another leg and square it, and it's equal to the hypotenuse squared. Call the legs and the hypotenuse whatever you want. But the idea is leg squared plus leg squared equals hypotenuse squared. Okay. But A, B, and C are the most common. Any questions on that? So, we've looked at the trig functions before when we did unit circle trig. Okay, we had like sine was y, cosine was x, tangent was y over x. Now we're going to define the 6 trig functions again, but we're not going to use the terms y and x. We're going to use the terms opposite, adjacent, and hypotenuse. I'll show you in a second how unit circle trig and this kind of trig are exactly the same thing. There's no difference. You're just using different names. But the sine, the cosine, and the tangent, they're all fractions. Specifically, they're fractions of a length divided by another length. Sine is the length of the opposite divided by the length of the hypotenuse. Cosine is the length of the adjacent divided by the length of the hypotenuse. And tangent is the length of the opposite divided by the length of the adjacent. Now, think about that for a second. Somebody give me a unit that we use for length. A unit. Feet. So let's say you had an opposite side of 4 feet and a hypotenuse of 5 feet. When you divide 4 feet by 5 feet, what cancels out? Feet. So the unit is gone. So what that basically means is whenever you write one of these trig functions, there is no unit. The unit is feet divided by feet, inches divided by inches, and it's gone. All right? So the number that you put right here is just a pure number. It has no label attached to it at all. Now, this number right here, oh yeah, that has a label attached to it. That's an angle. Cosine of some angle. What are the 2 units that we attach to angles? Either, yep,
Degrees or radians?
Degrees or radians, right? So that number has a label. But the answer that you get, no label. Now, we have sine, cosine, tangent. We also have these 3. Cosecant, secant, and cotangent. What's the connection between the one on the left and the one on the right? And
Inverse?
Not inverse. Not inverse. Different word. Reciprocals. What can you say that more simply? What does reciprocal mean? That's a fancy word.
Opposite? Or
Opposite is different. Opposite is like positive 4, negative 4. That's opposites. But these aren't negative and positive. They are reciprocals, which means, reciprocal means what?
You flip the numerator and denominator.
Yeah, if you have a fraction, you flip. So if sine is opposite over hypotenuse, cosecant is hypotenuse over opposite. Brandon, what about secant? Hypotenuse over adjacent. And Jacob, what about cotangent? So opposite over adjacent, that one's tangent. But what's the connection between tangent and cotangent? Jared told us a second ago. They are... Say it again.
reciprocal?
Yep, reciprocals. So if these are reciprocals, then what would the cotangent be?
Adjacent over opposite.
Yep, adjacent over opposite. Like Zach said earlier, you just flip it. Now, hypotenuse, that term is easy to describe. It's just the side across from the 90. Opposite and adjacent, those are a little bit different. Opposite and adjacent are what we call relative terms. Okay, another example of terms you guys know that are relative are left and right. Left and right don't always mean the same thing. It's relative to which way you are facing. So for me, left is the door, right is the windows. That's not true for you, because you're facing the other way. For you, right is the door, and your left side is the windows, right? That's like opposite and adjacent. They are from a certain perspective. So, if you had a triangle, and you put theta right there, that's your perspective. Pretend you're standing right there looking out at the triangle. What side do you think is opposite in that diagram? The height or the base? Yeah, height. That's adjacent. Right? Now, what if I do the same triangle, but put theta up there? Okay, what I've done is I've changed the perspective. You're standing in a different spot. Which side would be opposite now? Yeah, base. And this side is adjacent. So opposite and adjacent are not all, you can't just say, oh, the opposite is always the height. No. That's like saying left is always towards the door. No, depends which way you're facing. Right? So that's what I mean by they're relative. Now, if you have two triangles and all the angles are the same, it doesn't mean they're the exact same triangle. What it does mean is the triangles are similar. They're similar. Okay? Another way to think about similar is to basically think a larger or smaller version. Right? So if you draw something on a piece of paper, and then you put it on like a photocopier and enlarge it, it's similar. It's proportional to the original, but it's a larger or smaller version. So, the reason that's important is because we're going to look at something like, I'm going to scroll back up. We're going to look at something like this in a second. Look at those two triangles. First of all, are they similar? Chris, how come? Yeah, one of them is double the size of the other. That's all. So they are similar. So the question is, if we take one of these trig functions, like sine, and then we fill in an angle, like 30, the sine of 30 degrees should always be the same. It doesn't matter if you're using a small triangle or you're using a really big triangle. The sine of 30 degrees always has the same answer. And I'm going to prove that to you using similar triangles. Okay? So that's the idea. The trig functions we just wrote on the other page always have the same answer for a given angle. I don't care if you put a 30-degree angle and a triangle the size of the state. It doesn't matter how big the triangle is. All that matters is the angle itself. So let's look at actually doing that. Let's find the sine of 30 in this triangle on the left. And everything here is correctly labeled. Okay, so all those numbers are correct. Nikira, can you remind us what the definition of sine was as a fraction? Yeah, and I'll come back to this. I should have mentioned this to you guys, but there's a trick to remember them. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Has anyone ever seen that before? Sakatoa?
Physics.
Yep. So that's one way you can try to remember the three basic trig functions. I asked one year in a class, does anyone know the trick to remember the trig functions? And someone said Sacagawea. Sacagawea is not going to help. But Sakatoa will. So if you remember Sakatoa, it kind of helps. All right, so let's find the sine of 30. Opposite over hypotenuse. What side is opposite the 30 in the triangle on the left?
2. Oh, 1.
1. And what's the hypotenuse? 2. So the sine of 30 degrees is 1/2 in the small triangle. Now let's find the sine of 30 degrees in the big triangle. What side is opposite the 30? 2. And what's the hypotenuse?
4.
And what's 2 over 4 reduced to?
1/2.
1/2. That's why if I bring up my calculator and put it in degrees and I type the sine of 30, the calculator has no idea what size triangle I'm using. All it knows is I typed in 30 and I hit enter and it doesn't care what size triangle it is. The sine of 30 degrees is always 0.5. Has no connection with the actual size of the triangle. Okay. Any questions on that? All right. So, next we're going to look at something like this. Okay, don't write it yet because I'm going to tell you how to do it. I'm going to tell you one of the 6 trig functions. In this case, I'm giving you the sine. And I want you to figure out all the other ones based on knowing that one. If I tell you the sine Can anyone tell me specifically what pieces of information I'm giving you?
Yeah,
What?
because it's always the same.
Okay, so the definition of sine is always the same. So what two specific things have I told you by saying that? I have told you that the opposite side is 5 units, and I've told you the hypotenuse is 6 units. Well, I haven't told you the adjacent, and you're going to need that. How can you find the adjacent? Yeah?
Pythagorean.
Right, you can use Pythagorean theorem. So the idea is to find the 6 trig functions if you're given one of them. Take what you're given and use it to label two sides of a triangle. In the case of sine, it's opposite and hypotenuse. If it was cosine, you would know adjacent and hypotenuse. Okay? Label whichever two sides you know, and then use the Pythagorean theorem to find the third side. Okay? Now, at this point, you have all the sides of the triangle, and you can find anything you want. You don't really have to copy that last 3 lines or so. But I'm just saying, now you've got all the information. You can do all 6 trig functions. Okay, so just summarize it quickly. Label the two sides that you know. Use the Pythagorean theorem to find the third side. That's what you have to do. All right, so looking at that problem, sine of theta equals 5/6. I want to make a chart. What sine, cosine, tangent, cosecant, secant, cotangent. Oops. Now, do we know how big theta is? Do we know the angle that's being plugged into the sine function? No. You don't need to. Some people get a little confused, like, well, how can you describe 6 things about an angle you don't even know what it is? It's the same way you could describe a person if you don't know their name. I can just look at somebody and describe what color shirt they're wearing, hair color, eye color. I don't need to know their name to do any of that. I don't need to know how big this angle is to describe the sine of it. It's not necessary. So, sine, we already know. That one is 5/6. And technically, what other one could you write down right now without having to do any work, really? Yeah?
6/5.
Is which one?
Cosine.
Cosine is going to involve adjacent. We don't know that yet.
Cosecant.
Cosecant. Those are the only two that you can do without finding the adjacent. So now let's set up our triangle. And Sam told us earlier that 5 was opposite and 6 was hypotenuse. Now you might look at that and say, how did you decide to put theta on the bottom? Why not put it at the top? It doesn't matter. It doesn't make any difference at all where you put it. As long as wherever you put theta, the side opposite is 5. That's all. All right. So let's find that third side. How would I, somebody tell me how I would set up my Pythagorean theorem to find the third side there. And for now, let's just call the third side A. What would be my equation I would set up? Yep.
A squared plus 5 equals 6.
A squared plus what?
5 squared equals 6. Squared.
Squared. So A squared plus 25 equals 36. Okay. How about Elias? What would I do next to start to get A by itself?
Subtract 5.
Subtract 25 and 36 minus 25. 11. Last step. Kaya, what would be my last step? Yeah, we're going to take the square root to get rid of the exponent square. Now, generally, we do not write this as a decimal. When we start actually, when we start doing some other stuff tomorrow, we'll use decimals. But for today, we're just going to leave that as square root of 11. Don't worry about the decimal. Okay, so now we can write our cosine. Can somebody tell me what is the cosine of theta?
Square root of 11 over 6.
Now, is that okay for a final answer? I mean, is there anything wrong with that?
No.
No? That's fine. Nothing wrong with that at all. Let's look at tangent. What would my fraction for tangent be? Yeah.
I thought you did. 5 over square root of 11.
So I've got 5 over square root of 11. Is there anything wrong with that as a final answer? Yeah? Square root can't be in the bottom. Can't leave it like that. It's not wrong, it's just not done, right? So there's a little bit, you get like partial credit for that. So what do we multiply the top and the bottom by to fix having that square root of 11 in the bottom?
Square root of 11.
Yep, square root of 11 over square root of 11. That gives you 5 square roots of 11 over 11. Right, so we got that, and that. Now, I'm going to circle this in red because that's what we originally had. We're going to come back to that. That wasn't the answer. That's why I circled it in red. But I'll come back to it in a second. Let's do secant. Anyone tell me what you get for secant as a final answer? Yep. Yeah. Perfect. She flipped it and she fixed it so the square root wasn't in the bottom. Now, for cotangent, you got two things you could flip. We had what was circled in red to start with, but then we changed it to what was circled in black. Which one of these do you think would be better to flip? They're the same, but one of them is easier than the other. Yeah? Why would you flip the one circled in red compared to the one in black?
Square root cannot be in the bottom.
Okay. But this one in red has a square root in the bottom. Why do you want to flip that one? Yep.
This is the original.
Why is the original better?
Because the other one was simplified.
Wouldn't it be better to use something that's simplified? Prove me wrong. Yeah, I am wrong.
Since the square root's in the bottom, since you're flipping it, you don't have to do any math afterwards.
Right. If you flip something that has the square root in the bottom and make it square root of 11 over 5, you're done. If you took this one that was in black and you flip it, now you have 11 over 5 square roots of 11. You just put the square root back in the bottom. You've got to fix it all over again to get the same answer. So I would flip the one where the square root is in the bottom, and that's why. All right. So those are the 5 trig functions. Okay. Let's look at this one. Does anybody know what the hypotenuse is going to come out to there?
Mm-hmm. 13.
13. So what I was checking to see is if anybody knew that that was a special pattern. Like a lot of people know 3, 4, 5 as a right triangle. Okay, that one's easier to remember. 5, 12, 13 is another one. That's called a Pythagorean triple. When all the sides don't have any decimals in them and they're all nice. Okay. So If you knew that, you could write 13 right away. If you didn't, it's not a big deal. You can use Pythagorean theorem to figure it out. What's nice about a Pythagorean triple is you don't have any square roots. So you're never going to have to worry about a square root in the bottom. Okay. So start with sine. Jacob, what's my sine here? Think back, what's the definition of sine? It's what side divided by what side?
It's opposite side by pi.
Yep. So in this case, what are those two numbers?
0.3.
You don't have to do it as a decimal. You can just leave it as like whatever number you have in the top divided by whatever number would be in the bottom.
Oh, that's right, by 13.
Yeah, just leave it as 5 divided by 13. Okay. You don't have to do decimals till stuff we get to tomorrow. Okay, so there's your sine. How about Sam? What about my cosine?
It would be 12.
Yep, 12 over 13. And Jared, what about my tangent?
5 over 12.
5 over 12. Now, Nakira, what would you do with those three to get the next three? You just flip them. So 13 fifths, 13 twelfths, 12 fifths. Very, very nice to flip. Again, no square roots makes it easy. Okay. Any questions on that? Okay. All right, so let's see if we can use this diagram to find the 6 trig functions of 45 degrees. So the only difference in this problem is now you actually know the angle that you're working with. Big deal, doesn't really matter. What you really need to know is all the sides you're working with. So Kaya, what side am I missing in that triangle? Yeah, I'm missing the hypotenuse, right? And Emily, to find the hypotenuse, how would I do that? Yeah. And if you found that, what would be the hypotenuse? Well, if all the sides were 1, then what kind of triangle would it have to be? It would have to be equilateral, which would mean all the angles would have to be the same. Square root of 1? Is that what you said? That would still be 1. So, Chris?
Maybe square root.
Square root of 2. Right? 1 squared plus 1 squared is 2, and then add them up and take the square root. Don't worry about what the square root of 2 is. It's 1.4, but you don't need that. Just leave it. Now, you have to do everything from the perspective of the angle they're telling you to. What angle are they telling you to do what angle is your perspective here?
45 degrees.
45. It doesn't matter which one you choose because these two sides are the same. So pretend like you're standing at the bottom and go through all the trig functions. Okay. Sine of 45. Brianna, what would the sine of 45 be? Yep, 1 over the square root of 2. And Brandon, when I fix that, so it's doesn't have the square root in the bottom, what would that give me?
1 square root 2.
Perfect. 1 square root of 2 over 2. Let's look at my cosine. Jacob, what would my cosine be?
1 over square root of 2.
Yeah, it's exactly the same as the sine. Cosine is 1 over the square root of 2, so I'm just going to write square root of 2 over 2. So that's kind of nice when you get two answers that are the same, because then you're going to get two more answers that are the same in a second. And how about, Nikara, what's my tangent? What's the definition of tangent again? It's
Opposite and adjacent.
opposite over adjacent. Yes, that is correct. So what side is opposite the 45?
The 1.
The 1. And what side is adjacent to the 45?
The 1.
The 1. So it's 1 over 1, which would just give you 1. Now, to get the other three, we just flip them. Just remember which one you're flipping and what the name of it is. Jared, what's the name when you flip sine?
Cosecant.
So cosecant of 45 equals, I would flip this one right here, square root of 2. Now, if the cosecant is 45 degrees, is square root of 2, well then so is the secant. If sine and cosine are the same, so are cosecant and secant. And how about cotangent of 45? What would that be? For cotangent?
Oh, wait.
Yeah, 1. Because the tangent is 1. Think of it as 1 over 1 if you really want. 1 over 1, when you flip it, it's 1 over 1 again. So those are your six trig functions for a 45-degree angle. All right. Let's look at this one. Let's try to find, yeah, it's almost done. Let's try to find the 6 trig functions of, let's just do 30 degrees. Okay, what kind of triangle do I have on the board right now? Equilateral. Is that a right triangle? No, I want to make it a right triangle somehow. Now, first, if it's equilateral, that means all the angles are the same. But specifically, what are they?
60 degrees.
They're all 60s. Now, does anybody see what I could do in this triangle to basically create a 30, 60, 90 right triangle? Something I could do to it. Yeah.
Half one of the values.
I'm thinking like something like geometric. I want to add in something to it to create a right triangle. And I also want that triangle to have a 30, 60, and a 90 right triangle. I got to add something to that picture. Yeah. Yeah, draw in, there's a couple names for it. You could draw in what's called a perpendicular bisector or an angle bisector. I'm not going through the proof, that's geometry. But if you draw in an angle bisector in an equilateral triangle, it automatically cuts the opposite side into two equal lengths. Okay? So what that basically tells me is that this side, you know what, I'll sketch it over here. Let's go like this. That was 2. That side is still 2. That side is 1. That's 90 because we drew in an angle bisector, which also is perpendicular to the opposite side, at least in an equilateral triangle. That's 60. That's 30. And what would, how would I get my height of that triangle? What would I have to do?
Pythagorean theorem.
Yeah, just do the Pythagorean theorem. X squared plus 1 squared equals 2 squared. So you get x squared equals 3. Square everything and subtract the 1. And then take the square root of each side. So this is the square root of 3. Now from here, you're doing exactly the same thing you did in the last problem. We're not going to do all 6. Let's just do the first 3 since we did all 6 in the last problem. Now you have a choice here about the perspective. Is everything here from the perspective of the 30 or from the 60?
30.
Right, they tell you in the problem 30. So you're going to pretend like you're standing right there. So let's start with the sine of 30. In fact, this is one I did earlier when I was showing you guys similar triangles, a big one and a small one. What's the sine of 30?
One over.
Yeah.
1/2.
Yeah, 1/2. Opposite over hypotenuse. How about the cosine of 30? Chris? Square root of 3 over 2. Yep. And how about the tangent of 30? Yep.
1 over 2?
Let's see, cosine.
Oh no, 1 over square root of 3.
So yeah, opposite over adjacent, right? 1 over the square root of 3, which when you fix it, is square root of 3 over 3. Right? And once you get the first 3, you just flip them to find the next 3. Any questions on that? All right, so the last thing we'll look at has to do with complementary angles. You guys already answered my question here earlier. Right? This says that two acute angles are complementary if they add up to 90. Okay? And I asked you, and I pointed to one of the angles, and I said, why is this angle right here always between 0 and 90? Why is it complementary? And we said, well, it's a right triangle, and you already used 90 there, so then the other two have to add up to 90. Okay? So we already answered that part of the question. Here's the diagram that we're going to use a lot tomorrow. Anytime we have a triangle and we don't know something about it, those are the labels I want you to use. I want you to use A, B, and C for the sides. Specifically, I want you to use C as the hypotenuse. And I want you to use Greek letters for the angles. Now, that's not how our book does it. The reason I do it that way is because if you use lowercase and capital letters, that gets confusing. Especially like if you use like a capital C and a lowercase c. I can't really tell on paper sometimes if a C is capital or lowercase. Like an A I could or a B, but not a C. Right? And we're used to using C for Pythagorean theorem. A squared plus B squared equals C squared. So we don't want to change that. So we still want to use C for the side. But angles are always going to use Greek letters. Right? That also helps if you said to me, I don't understand how you got B. If you say you don't understand how I got B, I know you're talking about a side. If we're using lowercase and capital letters and you said I don't know how you got B, I have to say which one? You mean capital B or lowercase b? Which one are you talking about? So it avoids that confusion. Right, so that's your kind of generic diagram. A is always across from alpha. B is always across from beta. That's what you have to make sure you set up. A across from alpha, B across from beta. Alright, so let's go like this. It's not going to be any numbers here, it's just going to be letters. But I want you to notice something. What's the sine of alpha? What divided by what? Yeah? A divided by C. Now, watch what I'm going to do here. I'm going to put the word co in front of the function I just used. Cosine. And I'm going to use the other angle, which remember, these two angles add up to 90. So what did we call them? They're complementary. So I did two things there. I put the word co in front of that function, and I use the complement to alpha. Putting co in front of sine gives me cosine. The complement of alpha is beta. Okay. Now, what's the cosine of beta? What over what?
The adjacent over the hypotenuse.
And what's the adjacent?
A.
A. And what's the hypotenuse? C. Came out exactly the same. The sine of alpha is the same as the cosine of beta. Came out exactly the same. Okay, we'll do one more. Let's do tangent of alpha. What's the tangent of alpha? Chris? A over B. Now I'm going to do the same two things again. I'm going to put the word co in front of tangent. What do I get if I do that? Cotangent. What angle is complementary to alpha in that triangle?
Beta.
Beta. Now, think about cotangent. Cotangent is adjacent over opposite. From beta, what side is adjacent? A. What side is opposite? B. Again, came out the same. So this is a pattern called the complementary angle theorem. It's going to be the last thing we look at. Very simple theorem, very short. Complementary angle theorem says cofunctions of complementary angles are equal. Okay? Cofunctions. What are cofunctions? I just showed you what cofunctions are. I'll put a little note above it. Cofunctions. Sine, put the word co in front of it. Cosine. Another pair, secant, put the word co in front of it. Cosecant. The third pair, tangent, put the word co in front of it. Cotangent. Those are the three pairs of cofunctions. They're not paired the same way we do reciprocals when we flip, except the last ones. But the other ones are different. Sine, put the word co in front of it. Cosine. Secant, put the word co in front of it. Cosecant. Tangent, cotangent. So, point is, if you have cofunctions, like tangent and cotangent, and you have angles that are complementary, alpha, beta, then they come out equal. That's what I tried to show you in a couple different examples. You get the same answer. So, I'm going to show you how to use that to simplify something very, very easy without a calculator. Sine of 35 minus cosine of 55. First of all, I want you to look for the pattern here. Sine, cosine. What did we just call those? Sine and cosine are what? They're cofunctions. Okay, so we got that part. They're cofunctions. 35 degrees, 55 degrees. What kind of angles are those? 35 and 55 are, they're complementary because they add up to what? 90. So what you have here are cofunctions of angles that are complementary to each other. So we know that cofunctions of complementary angles are the same. So what would you get if you subtracted those two things? 0. I have no idea what the sine of 35 is. It's not a multiple of 30 or 45, so it's not an easy number for me to do in my head. I have no idea what the cosine of 55 is either. But what I do know is if you subtract two things that are the same, you always get 0. Doesn't matter what they are. They're the same, subtract them, you get 0. Is there any other operation where if you do the same thing and the same thing with this operation, you automatically know the answer? So subtraction is 1. You subtract the same thing from the same thing, you always get 0. There's one other operation. You do the same thing and the same thing, you always get something. Yep.
You divide by the same thing, you always get 1.
Right. If you have a division problem, and you divide two things that are the same, you always get 1. Okay. Let's check if these are the same. Tangent, cotangent. What kind of functions are tangent and cotangent? Co-functions. What kind of angles are 20 and 70? Complementary. Question over here, Eric? Co-functions of complementary angles are always what? They always come out the same. So if you divide two things that are the same, what do you get? 1. Now, would that idea work with addition? If you add two things that are the same, do you always get the same thing? You get the thing doubled. So it depends on what you started with. How about if you multiply two things that are the same? Do you always get the same thing? No. 2 times 2 is different than 5 times 5. So that's the complementary angle theorem. It only works in this very, very, very specific situation. If you change 20 to 21, well, then it doesn't work. Okay? So the homework tonight, most of it's in the book, but the last 2 problems, we have to copy those down. They're like what we just ended with in class. Don't forget, tomorrow we'll finish up this section. I will be after school Thursday. If there's anything you have to get done before Friday, Thursday's the only day to do it after school.